Hi, my name's Ben Purston and I'm an application scientist for molecular spectroscopy at PerkinElmer. Economically motivated adulteration of food ingredients like milk and milk powder is now a well-known issue. There have been many reported cases of dishonest producers adding nitrogen-rich chemicals like melamine in order to boost the apparent protein level of the product and thus the price they can demand. Now, this is a complex problem that needs to be tackled with a range of techniques, including rapid screening tests as well as definitive ones, which can be expensive and time-consuming and often not practical for high-throughput testing. So near-infrared spectroscopy is already widely used to check ingredient identity and nutritional properties, so it makes sense to use the same instrument for adulterant screening. Previously, there have been two available approaches. The first is to prepare a series of calibration standards with different concentrations of the adulterant, measure the spectra, and then develop a quantitative model for the adulterant. Several publications have shown that this is an effective technique for melamine, but the limitation is that the method development is very time-consuming, and in the end, you have a method that is specific to just one adulterant. If the sample is adulterated with something different, you might miss it. And that leads to the second method. Now, the real strength of near-infrared spectroscopy is that the spectrum is characteristic of the whole sample. So we can build a qualitative model for what normal milk powder looks like, and then look for deviations in the sample spectrum. This lets us do non-targeted screening for any adulterant, not just the ones we know about. The disadvantage with the second approach is that because we're not using any information about the spectrum of the adulterant, we don't get the same level of sensitivity as a targeted quantitative method can achieve. The solution we have developed, which we call Adulterant Screen, aims to take the best aspects of both of these approaches. The algorithm requires 3 sets of data. The first is a library of spectra representative of the material, uncontaminated milk powder, maybe 20-30 samples. The second is a library of spectra of potential adulterants in their pure form. There's no need to prepare mixtures of the adulterants with milk powder. And the third piece of data is the sample spectrum. The way the method works is that it uses the library of uncontaminated spectra to build a model of what a milk powder spectrum looks like, taking into account the natural variation between samples, which is due to compositional or physical differences. Then, we see how well the sample spectrum fits into this model. If it's significantly contaminated, then there will very likely be a large residual. Next, the software runs through the library of adulterant spectra and includes each one into the model. If, as we do so, the fit to the sample spectrum greatly improves, that indicates that the adulterant may be present in the sample. Now, the advantage of this approach is that we improve sensitivity by using the adulterant spectrum, but it doesn't require us to prepare a large number of standard samples for each adulterant. And that means that we can cast the net much, much wider. So let's take a look at how easy it is to use. First, press the appropriate app icon in Spectrum Touch software. The first screen displayed is an introduction screen, so press Next to continue. On the sample information screen, we enter the name of the sample and designate the sample type as either skim milk powder or whole milk powder. Then press Next to continue. The next screen displays sample preparation instructions. In this case, all we need to do is transfer some milk powder to a clean glass petri dish, tap the dish to level the sample, and then place the dish on top of the sample spinner. Then press the Go button on the instrument to start the scan. The system will now scan the sample and then calculate the results for the qualitative, quantitative, and adulterant screen methods. The next screen displayed is the results screen. Here we can see that the sample has passed the identity check, all the quantitative parameters are within their expected values, and there are no adulterants detected. So now let's run a second sample, one that we know to be contaminated. As before, we enter the sample information, place the sample in a petri dish on the instrument, and then press the Go button. This time, we see that even though the sample has passed on the nutritional metrics, it has failed because of an identified adulterant, in this case, urea. So our easy, rapid screening test by near-infrared has identified a potentially contaminated sample. At this point, the sample would be sent for a more definitive analysis, such as with the PerkinElmer Axion TOF-MS. This example shows how you can take near-infrared spectroscopy beyond quantitative methods for nutritional properties. Adulterant screen software from PerkinElmer lets you create simple, sensitive, and easily adaptable methods to extend your screening capability to address both present and future threats to food safety.